Hi, this is Professor Jim A. Chen at California State University, Long Beach. In this video lesson today, we'll look at transformations of functions, in particular, how we stretch and shrink functions. This is a continuation of the other video, which was on the transformations of functions, part 1. We also will look at the properties of even and odd functions. Let's start by looking at the vertical shrink or stretch has on the algebraic expressions of the functions. We start by looking at a very well-known function, which is absolute value of x. So for example, when x is equal to negative 4, I simply just get positive 4. And if it's negative 3, I would just get 3 there. If we look at one modification of that function by simply multiplying it 2 to the entire quantity, well, what effect does it actually have on your y value? Well, that's essentially doubling your y value. So before it was 4, now it becomes 8 when x equals 4. And then when it was 3 there, we're going to double it into a 6. And everything else, as you can tell, is simply just a doubling of the previous y value. The third graph we have here is changing the multiplier from a 1 to a 1/2 on the absolute value function. And the effect that it accomplishes is halving the y value we have. So when x equals 4, we have the y value of 4 there. It's just going to be a 2, and half of the 3 would then be 1.5. And everything else, as you can tell from the chart, is just going to be half of the original values. So if we want to write a formula for f of x and h of x in terms of the original well-known g of x, what would we write? Well, f of x is the double amount of the g, right? Because just doubling the y value. And h of x is halving the original amount of g. So that would be kind of a generic or general recipe that we would get from the original function g. But what effects do these halving and doubling have on the graph of the function? We'll start with the first one, f of x equals 2 of g of x. For every y value we have on the x point, we're going to double that. So for example, when x is equal to 1, the original y value is at 1 on this blue dot, which is going to double that, which makes it into a 2. The x equals 2 has the y value of 2, we're going to double that into a 4. X equals 3 has the y value of 3, we're going to double that into a 6, and so on. If you double every single y value, this is what you would get. And I'll go ahead and finish that on the left hand side here as well. So the picture we get is the same shape of the absolute value function, v shape. So the shape that we get for the f of x is exactly the same as the absolute value v shape graph, except it's a stretched version of it because it covers more y value for the same amount of x values. Here, the x values on the right hand side going from 0 to 4. Before, on the original function, it only covers up to 4 in the y value, but now actually stretched out into a more coverage in the y direction, goes all the way up to 8. So that's why we say this is a stretched version of the original one, and vertically by a factor of 2. On the other hand, let's graph the function h of x, which is halving all the y values from the original g. So when x equals 1, it has the y value of 1. I'm going to half that, make it into a half. When x equal to 2, I have the y value of 2. I'm going to half that into a 1. 3 is going to become a 1/2. A 4 here is going to give us a value of 2, and so on. Let's complete the opposite side as well. If we connect the points, we would get also the same v-shaped absolute value function graph, except that it's now shrinked a little bit because there's less coverage on the y direction. So I would say that multiplying g of x by 1/2 actually has the effect of shrinking vertically by a factor of 1/2. If you ever have trouble deciding whether or not your graph is a stretched version or a shrunk version, I would suggest that you look at the word vertically, because you're trying to see how much coverage vertically you actually gain or lost. So a stretched version would be you actually gain more coverage in the y direction, the vertical direction, and shrink would then be losing coverage in the y direction. Sometimes you also hear that a stretched version of the graph corresponds to a narrower graph, and a shrunk version of the graph corresponds to a wider graph. And those references really are talking about more on the horizontal point of view. A narrow graph is you actually have a less coverage in the horizontal, less coverage in the x directions. A wider graph actually has a wider coverage or a bigger coverage in the x direction. So they're really two different things depending on which directions we're talking about. Next, let's consider an example of a horizontal shift and stretch. Here I'm giving you a function of g of x on the blue dotted line. I want you to graph a function that is shrunk horizontally by a factor of 1/2. And what that means is for every x value that you see there, you're going to share the same y value there, but then for a half of the x value. So the y value here is at 2 is going to be the same as the x value at 1/2. For the x value at 2, you get the y value at 5. We're going to share that same y value there for half of the x value, which is at 1. Okay, try to finish for the rest, see what the graph you get. So I got this picture, which is exactly the same parabola, but now kind of squeezed or shrunk by a factor of a half in the horizontal direction. So you notice that shrunk, meaning there's less coverage, but in the horizontal directions, meaning in the x directions you actually have a less x values corresponding to the same set of y values. So if you try to fill in the blanks down here, we see that f of -1 is the y value at x equals -1, which should be the same y value before doubling the x value in the original, because this is a shrunk version. Remember, that's a half factor of the original one. So if you start with the -2, a -1 would be a half of that. Okay, same thing, f of 2 would then be the same as g of 4. So you can try to fill out the rest of the blanks here using the notation of g. If you're not sure, you can also verify that from the graph. Remember, if you go locate f of 1, it would be this point, and that should be the same y value as the g, but at this point, which is at 2. So in conclusion, the function f of x equals g of 2x has the same graph, except that g of x was shrunk horizontally by a factor of 1/2. Well, you might be a little bit confused at this point, like why when we shrink horizontally by a factor of 1/2 actually corresponds to doing 2 times in the input value in the function g. Well, in general, if you want to graph g of a cx, where c is any constant, and you can think of c as kind of your stretch factor or shrink factor, it turns out that if c is greater than 1, then it has the effect of shrinking the graph of f horizontally by a factor of 1 over c. In this case, our c is 2. That's why it has the effect of shrinking the graph of f horizontally by 1 over 2. On the other hand, if c is between 0 and 1, then it has the effect of enlarge or stretch the graph horizontally by a factor of 1 over c. So for example, g of 1/2 x would then be the result of stretching the original function g by a factor of 2 horizontally. Now to answer this example should be fairly straightforward. If I wanted to get a graph that is a stretched version by a factor of 2 horizontally, I would simply just do g of 1/2 x. Alright, take a moment and try to write a formula for the function whose graph is the same as the graph of g except shrunk horizontally by a factor of 1/3. And the answer should be f of x equals g of 3x. Now so far we don't really have any description of the function g, so I can't really turn it into anything else. So at this point, letter g would appear in the formula. But as soon as I actually tell you precisely what this function g is, I should not expect to have a letter g in the formula at the end. Okay, so go ahead and use the recipe that we got from the previous step to write a simplified formula for the function f. The recipe says it's going to be g of 3x, which means that I'm going to replace my input by this new input of 3x there in the function g. So I will get 4 over the entire quantity 3x raised to the power of 2. If we simplify this, I will get 4 over 9x squared. It turns out that for this function, shrinking the graph of g of x horizontally by a factor of 1/3 gives you the same picture of shrinking the graph vertically by a factor of 1 over 9. Why is that? Well, if you look at the expression that we got, I can think of this as 1 over 9 times the function 4 over x squared. Right? And then notice that this 4 over x squared is our original g. So I can think of this as 1 over 9 times the g of x. And we know this from our previous discussions that multiplying a 1 over 9 front reduces coverage by a factor of 1 over 9 in the y directions, and that corresponds to shrinking vertically by a factor of 1 over 9. Now that we've discussed all different transformations we can apply to a function, including translations in the horizontal and vertical directions and reflections about the x and y axis, as well as stretching and shrinking both horizontally and vertically, let's look at kind of just the overall picture and combining all of these ideas into this big example. This slide and the one afterwards is going to be just a huge practice for you to see if you've mastered all these concepts. Okay, so try to take a moment and go through each of those examples to see if you can do those by yourself and come back to check the answers. In these examples here, we're given a graph of g of x, and we were asked to find the formula for f if we do these actions to it. We wanted to get a algebraic description for it, as well as some verbal description of the effects that we accomplished here. So the first one here is given to you just to kind of get you started. If we shift the graph of g of x up by 2 units, well, that corresponds to adding a 2 in the y direction. So f of x has to be g of x plus 2. And verbally, that would mean add 2 to the output of g, because this entire thing is considered as the output of g, and then we just add 2 to that to accomplish the task. So now if I want to shift the graph of g down by 3 units, then I would get the graph f of x equals g of x minus 3, and that in words means I would subtract 3 from the output of g. Next one, if we shift the graph of g left by 4 units, that would then give me f of x equals g of x plus 4. And in words, I would say that's add 4 to the input of g. And this last one on the bottom here says reflect the graph of g across the x-axis. Well, then a function f of x would then look like negative g of x. And verbally, that would mean multiply the output of g by negative 1. If I reflect the graph of g across the y-axis, then the x becomes opposite, sharing the same y values. So I would get f of x equals g of negative x. And verbally, that means it's multiplying the input of g by negative 1. The next one is to stretch the graph of g vertically by a factor of 6. A vertical stretch is to gain more coverage in the y direction, and that can be accomplished by multiplying a 6 in front of the entire y value. So that's 6 times g of x. And verbally, that means multiply the output of g by 6. Similarly, if you want to shrink the graph of g vertically by a factor of 1/7, you just multiply by a 1/7 in front of it. And that is multiplying the output of g by 1/7. If I want to stretch the graph of g horizontally by a factor of 8, this is actually to gain coverage in the x directions, and to accomplish that, you actually multiply a 1/8 to the input value. So I would actually do f of x equals g of 1/8 x. And that's the same as to multiply the input of g by 1/8. So the last one here is to shrink the graph of g of x horizontally by a factor of 1/9. It's just going to be the opposite of what we've done there, multiplying the input here by a 9. The last set of discussions here is on the properties of even and odd functions. This concept of even and odd functions becomes really useful, especially when you have to deal with integrations of functions in a calculus class. A function f is called an even function if f of negative x is equal to f of x for every x in the domain of the function. For example, f of x equals x squared is an even function, since if I were to do f of negative x, I would get negative x quantity squared, and that turns into a positive x squared, which is exactly the function f of x that we started with, so it satisfies the definition. On the other hand, the function g of x, that is x squared plus x, is not an even function, since g of negative x is negative x quantity squared plus a negative x, which gives me x squared minus x. This is certainly not equal to the original function g of x for all the x values I can possibly pick. For example, if you simply pick x equals 1, then g of negative 1 would be 1 squared minus 1, which gives me 0. On the other hand, g of 1 would then be 1 squared plus 1, which is 2. And certainly 0 is not equal to 2. These two cannot be exactly the same. Hence, g is not an even function. The nice thing about even function is that the graph is symmetric about the y-axis. That is, the opposite x share the same y values. We can use that information to get the left portion from the right portion of the graph simply by reflecting the right portion across the y-axis. For example, the function y equals x squared that we looked at earlier, if I simply just draw the right portion of the graph, then I know to get the left portion simply by taking the mirror image of what's on the right. On the other hand, a function f is called an odd function if f of negative x is the negative f of x for every x in the domain. For example, the function f of x equals x cubed is an odd function since f of negative x gives me negative x quantity cubed, and as you know, when we cube a negative number, you still get a negative x cubed. And that's exactly the negative of x cubed, but we know that x cubed is the original f of x. So I can write this as negative f of x. Okay, so that satisfies the definition, and certainly this expression will be true for any x that I use there. On the other hand, the function g of x is equal to x cubed plus 1 is not an odd function, since g of negative x will be negative x quantity cubed plus 1, which gives me negative x cubed plus 1. And I can't really write this as the original x cubed plus 1 with the negative sign in front. In particular, this certainly is not equal to a negative x cubed minus 1 for all x. In particular, if x is equal to negative 1, then g of negative 1 is 0, while negative g of 1 will give you negative 2. 0 is certainly not equal to negative 2, hence we cannot possibly have the fact that g of negative x equals negative f of x for every x in the domain. The graph of an odd function is symmetric about the origin, which is obtained by reflecting across the x-axis first, then the y-axis next, or actually can be accomplished by simply rotating around the origin 180 degrees. So for example, to graph y equals x cubed, I could start by graphing the positive portion of x values first. To get the left portion of this graph, I can first reflect about the x-axis to get this picture, and then reflect again about the y-axis to get this picture, which means the overall picture of my function should be this. As a final note here, a function doesn't have to be even or odd, it could actually be neither. If it doesn't satisfy the definition for an odd function, it could be even or neither, but if it doesn't satisfy the definition of an even function, then it's neither odd nor even.